Thank you. Good morning. Thank you for this. It's great to be here. Thank you for the invitation in these wonderful surroundings. Okay, I didn't do anything, but it doesn't matter. So hopefully it doesn't change automatically. Do I say next slide or do you do it? I have to do it. Okay, I know how to do it. Yeah, it's fine. Yeah. Okay. So I'm going to talk about the quaternary, which is some people might think this is a rather megalomaniac undertaking to do it in 35 minutes. It probably is. I'm probably going to run out of time. I leave some time for questions. This is, in theory, the outline. Some transitions and some problems of cyclicities. Okay, let's start at the beginning. The intensification of Northern Hemisphere glaciation. So it goes back to 1977, Eastern Equatorial Core V28179. Nick, for the first time, observed that right above the Gauss-Matayama boundary, there was a shift in the amplitude of glacial stages into heavier values, and suggested this is where you started having this early Northern Hemisphere glaciation. Next step is 1984 in the North Atlantic, core at site 552A is the identification of the onset of ice rafting, and it's right about here. There's a change. What they saw in that core above the Gauss-Matayama boundary, you start getting this alternation of black sediments and light sediments. The light sediments were carbonate, and the black, when they looked at it, had IRD in it. So again, right above the Gauss-Matayama boundary, you start having this onset of Northern Hemisphere glaciation. And then I think then the story is complete in 1990 with this publication by Shackleton, Berger, and Peltier. It's ODP site 677, Eastern Equatorial Pacific, where that onset, again, above the Gauss-Matayama boundary is at stage 100. And in fact, in that paper, Nick suggested that new ages based on astronomical calibration for the various boundaries. So he suggested that the top of the Gauss should be moved from 2.47 to 2.6, which is pretty close to what it is. And just on a personal note, when they were doing that paper, they were in Cambridge. I was a lowly PhD student. I was not Nick's PhD student. For some reason, he invited me that evening to have dinner with the three of them. I was just sitting there observing these amazing people. Just as I think, you know, for your PhD students, make sure you invite them and you introduce them to all the people. They will never forget it. Okay, so next. And coming to more recent times, this is Bailey and co-workers in 2013. And what we see in more detailed of the ice rafting detritus in core 611 in the North Atlantic. So you have peaks at glacial G6, 4, 2, 104. You have single peaks of IRD, but then once you get to stage 100 is where you're getting multiple IRD peaks. That's where we start, and that's, I think, essentially also the start of this what we think of glacial Pleistocene glacials. Okay, now what's causing this? We don't know. Multiple hypotheses. I'm just going to go through some of them. Poleward migration of continents through time. Dynamic topography, so it's leading to an increase in the altitude, especially around the Baffin area side, so you can have nucleation, glacial inception in those areas. That's one idea. Then you have a whole series of hypotheses related to tectonic changes and for example, the emergence of the Panama Isthmus, changing the circulation in the North Atlantic, leading to to stronger North Atlantic circulation, delivering increased moisture supply to higher latitudes. Another one is the Kane and Molnar, the closing of the Indonesian Seaway, decreasing temperatures, sea surface temperatures in the Indian Ocean, and reducing heat transport to higher latitudes, and so the higher latitudes get colder. And then also, inevitably, you have an astronomical hypothesis. People suggested that there is this change in the amplitude of obliquity cycles. This is the long cycle of obliquity, 1.2 million years, that happens around the time, but you also have a change in the eccentricity, where you, between 2.8 and 2.6 million years ago, you have a change in the amplitude of precession, which is modulated by the 400,000-year cycle of eccentricity. So that happens around the time. I mean, you can pick and choose whichever change you want. There will be some change in astronomical at that time. And then, of course, there is the secular decline in CO2 that happens around that time, and we're not quite sure why. But when you put a gradual secular decline in intermediate complexity models, like the Climber-2 model of Vilate and Ganopolsky and Kalev, and what they see is that gradual decline in CO2 is able to move from glaciers with small ice sheets in the northern hemisphere to larger ice sheets. Okay, then you have to explain why the CO2. The end result of this is we don't know. There's all these various hypotheses. They're not necessarily alternative. It could be a combination of things. We don't know. Right, next point. So once you get into the Quaternary and you start having Pleistocene glacial cycles, we all know that if you look at the northern hemisphere summer insolation, 65 degrees north is here. You have about 120 local maxima, but then you only have about 50 interglacials. And so immediately you have a problem why you have fewer than 120. So in this part of the record, first we have the so-called 41,000-year problem. Insolation maximum every 21,000 years, interglacials, glacials every 41,000 years. So you can, for example, look this here. So here's one peak in the benthic delta 18 stack of, lighter values, but you have two insolation peaks in the intensity of summer insolation. Okay, so again, various ideas have been for that. I'll just pick on one. Ramo and Isansioglu suggested that this obliquity signal has to do with obliquity modifying the equator to pole insolation greater. So when obliquity is lower, and so the axis is more vertical, you increase the gradient between the equator and the poles, then so the poleward transport of moisture, which is important to build ice sheets, so you have increased accumulation. So this may well be one of the explanations. Another explanation is this. I need to take you through this. Some of you have seen this multiple times. I know it's boring, but we like this graph. Let me take you through this. So what we have is we started, here's present time, and we go back through time all the way to 2.6 million years. Okay, so you have all these panels. Shown in black is the insolation, and that's the Milankovitch metric. That's the caloric summer half-year insolation. It's important because Milankovitch used this metric because it has, at 65 degrees north, is about equal contribution of obliquity and precession. And one of the big things of Milankovitch, when he did his theory, was that obliquity is important in the high latitudes. Now, since that, what happened is that there's been, in the 70s, there was 60s, 70s, was a shift. People started using the summer solstice maximum insolation, which is dominated by precession. And there's a reason why that happened. I won't get into that, why André Berger started using this. So here we go back to the basics. Is the caloric summer half-year insolation in black. In orange, brown is the benthic delta 18 record stack of Lisicki and Ramo. Okay, then what we have, the dots represent, so a red dot is when you have an insolation that's associated with a complete deglaciation, with an interglacial, the red dot. The blue dots is when you have an incomplete deglaciation, so you have an interstadial. And then you have some black dots like here where you have a continued interglacial because in between, let's say, stage 7, there really wasn't a glacial inception. So it's just a very long interglacial because you didn't have glacial inception. But those are very few. So essentially it's black and is red and blue. Okay. Then the gray boxes represent intervals where obliquity is above average. It's above 23.3. This is when you have high obliquity. So first observation, all the red dots are in gray boxes. So all the red dots occur when obliquity is above average. But not all the gray boxes have red dots. So here you start skipping. So after the middle Pleistocene transition, you start skipping these gray boxes. But if we look at the early Pleistocene, this period here, all the gray boxes, I think there's one missing, all the gray boxes have a red dot. And why is that? So what is saying is that the 41,000 year cycle arises simply because every second insolation peak is boosted by higher obliquity. So for example, if you look at stage 21 here, you can see 2 peaks, but it's that first one that's a higher one because it's got higher obliquity in addition to the precession minimum. Okay, simple. Plus also ice sheets were smaller. We think, even though not everyone agrees with us, that it's probably they were smaller and confined to higher latitudes. So it's just obliquity was important. Okay. So that's the 41,000 year cycle solved, we think. Now, and then of course we have the middle Pleistocene transition. The middle Pleistocene transition suggests that we have a shift from the so-called 41,000 year world where glacial cycles became longer, stronger, and more so tooth-shaped. Okay, so what does this happen? And we'll spend a little more time here. I know Carla is going to talk a little bit as well about this. So I tried to put this together in a report that we made for Pages a couple of years ago after a meeting. And so what we have is you have a series of different hypotheses. One has to do with mantle convection here, another one ocean and atmosphere changes, and then something about ice sheets, land surface ice sheets. And then we have longer term changes and shorter term changes. And so the shorter term changes happen within one glacial cycle, probably around 900,000 years. So let me go through some of these. So one is this with the mantle convection. So there's the idea that you have a reduced mantle plume activity here that led to an increase in the depth. So it gets cooler, this Greenland-Scotland ridge, and starts getting deeper, so the increase in the depth of the Greenland-Scotland ridge increases, and that increases the Atlantic inflow, and so increases the Nordic heat pump, and that contributes to the growth of larger ice sheets. Now, this idea has been around for a long time, but it's been revived recently in 2021 by Steve Barker and co-workers. Then there was this other idea by Britannia and Van der Waal, that has to do with the coalescence of the Laurentide and Cordilleran ice sheets. So whereas the idea is whereas in the early Pleistocene, the Cordilleran ice sheet and the Laurentide ice sheet were separated and there was a corridor in between, then they started, those ice sheets somehow coalesced. And you have, well, here's the last glacial maximum configuration. And suddenly you start having much bigger ice sheets, and the bigger ice sheets are more difficult to melt, and so you start skipping insolation peaks, and that's why you get the longer cycles. Well, glacial geological work that's coming out of North America suggests that this coalescence of the Cordilleran and the Laurentide ice sheet is very recent, it's at the LGM. So the stage 6, big glaciation, the evidence suggests that it's different, the winds were different, and that there was a corridor in between that had not coalesced. And now it's also, this seems to be applying, this is work that's happening right now in stage 12. So the biggest ice sheet in the Northern Hemisphere did not have the Laurentide and Cordilleran ice sheet coalescing. If that's true, then this idea is out the window. Then, the regolith hypothesis. So this is going back to work by Clark and Pollard, David Pollard, and also Clark et al. 2006 in the Shackleton volume. And it's the regolith, and the idea that you have this loose and conformable sediments sort of blanketing the, especially North America, the regolith, which starts gradually to be eroded by the smaller ice sheets and more erosion and more erosion and more erosion. At some point, you remove completely the regolith, and then what you have is ice sheets that are just sitting on hard crystalline beds, and that changes the dynamics of the ice sheets, and then instead of spreading slowly, you have them growing up, and the moment you grow up, these thicker ice sheets have a different response to insolation forcing and more non-linear response. So again, you start skipping cycles. So you get bigger ice sheets because there's a change in the underlying geology, and the bigger ice sheets are more difficult to melt. You skip insolation cycles. Then there is a combination of things in Villate and co-workers 2019, again using that climber model that we saw earlier for the intensification of Northern Hemisphere glaciation. They impose this decrease in CO2. They say it's a decrease in the rate of outgassing. And once you do this, and you also apply a regolith, that you slowly remove the regolith, then you do get this middle Pleistocene transition and larger ice sheets. Note here that, of course, their ice sheets are larger than we think. There's no corridor between the two. And then there is what I call the Lamont view of the world. And the Lamont view is about this 900K event that all happens between stage 25, and then there's a skipped stage 23 insolation peak, and then you have this the first large glaciation in the Northern Hemisphere of marine isotope stage 22, 900,000 years ago. So the idea is that at that time, you have a reorganization of deep ocean circulation. So whereas before you have northern component water and southern component water is a shorthand for Antarctic bottom water, both interglacial and glacial, not a big difference. But then during the so-called 900K event, there was an increase in the southern component water, and then that changed the amount of CO2 that is stored in the deep southern component water, and then that led to cooling, and that's why ice sheets get larger. So then the next question is why would the change in circulation occur? And that goes back to an idea of Mo Ramo in 2006, that they said around this time, around 1 million years ago, you had a shift in the Antarctic ice sheet from terrestrial-based to marine-based. And so this idea of the marine-based is that it changes the whole stratification. There's less water that is being melted because there's marine-based than meltwater coming from terrestrial-based, and so there's a salinification and there's stratification, and then you start storing. You change the Antarctic bottom water and you store more CO2. Okay. And then there's this going back to this paper from 2017, to this diagram. The next, what we're going to do is going to take all these dots and plot them relative to insolation and the time elapsed from the previous interglacial. So here's the values of the caloric summer insolation, and this is the elapsed time since the previous interglacial. And suddenly what we see is there's a clear separation between the complete deglaciations and the incomplete deglaciations. And what you have here is this line is a threshold for deglaciation that is lowered as with time, since the more the time since elapsed since the previous interglacial increases, this threshold is coming down. What does this mean? It simply means that the ice sheets are getting larger and they become more unstable. The larger they are, the more unstable they are. That's an idea going back to McHale many, many decades ago. And then this slope of the line represents a discount rate, if you like, for deglaciation. Okay? And the slope has this value here. I'll come back to this, why this is important. So, what we're saying is that an interglacial occurs when a peak in insolation exceeds a threshold that decreases with time elapsed since the previous interglacial. So the dots are plotted for the last 1 million years. If we look at the earlier Pleistocene, and this was in the supplementary, so nobody ever looks at the supplementary, but we think is really interesting because when you plot, again, the complete deglaciation from the incomplete, you draw a line, and the slope is exactly the same. When we saw it, we thought this you know, no way. And this is not is a logistic model that is doing that. I mean, we didn't try to sort of fit it in ways. It just the model came up with the same number before 1.5 million years ago and after 1 million years ago. In between, there's too few points, so you can't draw a line. It's just you couldn't do it. And so, but what's important is that the y-intercept is lower. So the y-intercept here is 6.14. So it means how much insolation you need if you have 0 elapsed time. It doesn't happen, but you know. And then you need a lot of insolation to pull it if you have, you know, if you don't have any elapsed time. And here it's lower. Okay, so what does this mean? It means that during the course, when we plot all these dots over time, that there is this shift in the insolation threshold that's required for a complete deglaciation. So in other words, something that like here that was enough to have a deglaciation in this part is no longer enough. Why? Because we think the climate's getting cooler. So the same insolation boost is not enough. Is it getting cooler? There is quite a lot of evidence suggesting it is getting cooler in that we have changes in the northern component water. It's decreasing this way, so it means southern component water is increasing, not just around 900,000, but from 1.55 onwards. Southern Ocean dust, and before I go this, Site 1308 in the North Atlantic, this is bulk Delta 18. This is a proxy for IRD. Again, at around 1.5, it starts increasing. Southern Ocean dust and iron accumulation, which may have something to do with CO2, is also slowly increasing. So it may have something to do with the CO2 decreasing over time. So then what we're saying is that whatever the underlying cause, a gradual cooling and a gradual rise in the deglaciation threshold started about 1.5 million years ago, and this led to an increase in the frequency of skipped caloric summer insolation peaks after 1 million years, and the emergence of longer glacials allowed the accumulation of larger ice sheets and increasingly unstable ice sheets. Okay, let me explain what the difference is. So this is the complete opposite from the regolith hypothesis. And they say ice sheets get bigger, then you skip insolation cycles, peaks. We're saying because it's more difficult to deglaciate, you start skipping insolation peaks, and you have more time, and the ice sheets are getting larger. Okay, and there is some tangential evidence. This is from a conceptual model that Etienne Legrand and co-workers have done, and where they just used orbital forcing to reproduce glacial cycles, and then they changed the deglaciation threshold abruptly at one point, And then what they did is a sort of a gradual change, and the gradual change is able to reproduce this. It's not proof, but it sort of seems to suggest that there's more of a long-term change. So if we go back here, so we think there's some sort of cooling that happened over a long time, maybe after 1.5. And this may be related to a CO2 decline. So we're desperately in need of projects like Beyond Epica and other projects for the oldest ice from Antarctica to see whether this is happening. And when this, of course, is happening, then you have growth of Northern Hemisphere ice sheets. But it's also true that it may have also effect. This cooling is what led to the change in the Antarctic ice sheet that Mo Raymer invoked towards a marine terminating Antarctic ice sheets, which that in turn changed the Antarctic bottom water and the circulation in the Atlantic. Okay. So we stay tuned for what will happen in the next few field seasons in Antarctica. Right, so 100,000 year problem, 26 minutes, okay. This is more tricky than the 41,000. We all know what the problem is. The problem is that you have very little power in eccentricity, excuse me, here in the summer insolation, and yet in the last 1 million years, you have this 100,000 year cycle that appears, which suggests it's something to do with eccentricity. Going back to Hayes, Embry, and Shackleton, 1976, they already saw that. They said, we have a 100,000 year cycle. This probably is a non-linear response to orbital forcing because the ice sheets are big, and then they have a different time constant, and that's what's causing it. And then Embry in the spec map continued this in 1992, 1993. Then you have some ideas of that simply have internal oscillations of the climate ice carbon systems that are happening all the time, but then they're phase locked to the eccentricity cycle. And then you have a whole set of hypotheses that say that the glacial terminations occur in quanta of either the precession or the obliquity. So you need 2 or 3 obliquity cycles or 4 or 5 precession cycles. So it gives you the impression that it is 100,000, but it's really not 100,000. So a lot of people in this think, so they call it the eccentricity myth. You know, guys, there's nothing to do with eccentricity, it's an appearance. I used to think that, I no longer think that. You need to go back to Raymer, 1997, and this classic paper of the timing of the major climate terminations. And the main point of that paper was what she called the excess ice volume. So when she said that right before the major terminations, what you observe in the benthic delta 18 record is this increase in ice volume, and she called this excess ice volume, about 30, 40 meters higher, and that happens because you skip an insolation peak right before the termination. And the reason you skip them is because the eccentricity is at a minimum. So here, all these gray boxes show where eccentricity is at a minimum. And when you see that, it skips a peak right before the termination. And then you have, what you have is again the same idea of McHale that leads this excess ice. We build large ice sheets which are more unstable. And then the next insolation peak just pushes it over the limit. And in fact, Lorraine Lizicki in 2010, she did that in a more statistical way, and she found that there's this link with eccentricity. So I think this is why we get the 100,000 year cycle. So it accounts for the buildup of excess ice, but it does not account for the skipping of every insolation peak. It just accounts for the skipping of that last insolation peak. It does not account why this gets skipped, and this gets skipped because there's just not enough elapsed time from the previous interglacial. So you can't build large enough ice sheets. Whereas in the early Pleistocene was enough to have a deglaciation, in the middle and late Pleistocene it's not enough because you raise the deglaciation threshold. So it's a combination of things. So the low eccentricity accounts why we have 100,000 year cycles, but not why we don't have 41,000 year cycles. Okay, so it's a combination of things. Right, last point. The mid-Bruns shift, we call it it's known as the mid-Bruns event, the mid-Bruns transition, and we thought, last year, this time at Grenoble, we said, you know, we have the MPT and we have the MBT. It's not, so we call it the MBS, so the mid-Bruns shift, because it happens over time. So what is it? There is a shift in the amplitude of interglacials, so suggesting sea level was even higher after 430,000 years ago. Well, not in stage 7, but certainly in, you know, suggestion, or you have really complete deglaciations in 11, 9, and 5e, and 1. And also at the same time, you have this shift in the peak interglacial CO2 happening. And if you plot the delta 18 and the CO2, what you have is these warm interglacials here, but not stage 7. And stage 7 more plots here in the cooler interglacials. Okay, so the one explanation for this goes back to 2004, the EPICA community paper, which suggested, well, again, it's the obliquity cycle. It's the amplitude of obliquity that's slowly increasing around this time, and that leads to stronger interglacials. And then you have another set of explanations, starting with Yin, 2013, that essentially said, so small changes in insolation. We don't see any big changes around that time, but small changes in insolation lead to changes in the winds, in the southern westerlies, and the Southern Ocean ventilation, and it leads to cooler interglacials before. So you have stronger winds before the MBS, and then less strong winds after, and that makes them, you know, you go from cooler to warmer. And then Barth et al. Build on this, and they said essentially what is changing the Southern Ocean ventilation. They looked at the delta C13 gradient in the Atlantic and suggested that this changes this. So before the MBS, you have larger Antarctic bottom water formation, which stores more CO2, and then after the MBS, there's a decrease in Antarctic bottom water, and you have more CO2 degassing. Okay, could be. And then this last thing is this by Mitsui and co-workers in 2022, where what this shows is essentially a decomposition of the contribution of what contributes to the intensity of interglacials. Why interglacials? Some interglacials are stronger than others. So we suggested there's two reasons. One is how large the ice sheets were before. So let's go back to Raymo. Bigger ice sheets collapse, so they melt more completely. And the other thing is that if you look at the insolation integrated over the entire period of deglaciation, but both in the northern high latitudes and the southern high latitudes, that explains the intensity. If you just use the northern high latitude insolation, it doesn't. You need to use the southern high latitudes. And so when you do both, what you see is that there is a change in the contribution of insolation integral at both regions after the MBS. So you can see that all these interglacials have a strong contribution from the insolation at both regions. And we know that when you do integrate insolation in 65 degrees north and 65 degrees south, it cancels precession because it has an opposite effect, and it leaves obliquity, and therefore it's an obliquity thing. And it's that increase, so now time is going this way, so it's that increase in obliquity so go back to EPICA 2004, that may be right after all this. That's the long cycle of changes in the amplitude of obliquity that is causing this. Okay, concluding thoughts. So, if you have lots of experiments and you have, like the whole glacial cycles of the Pleistocene, then you can start building rules. So we did a rule in 2017. Andrei Ganopolsky last year had another rule in his generalized Milankovitch theory, which is not different. Steve Barker and I'm involved with this, a slightly different rule. You can find rules that can explain this, at least conceptually. The problem is what happens when you have a singularity, if you have just one, the intensification of northern hemisphere glaciation. you can find all sorts of, you can find changes happening around that time, but that confluence of event does not mean that you have, you know, a causal connection. So I think about the intensification of the hemisphere glaciations, I'm not particularly optimistic that we'll know what happened. And probably it's a combination of things. The MPT is interesting because it's not just a singular event. I think what I showed today suggests that there is a longer term thing. So maybe there is a thing of actually pinning it down, or at least getting rid of some of the hypothesis and so narrowing the thing. But that will depend on the CO2 record. That's it. Thank you very much.